So as we talked about synthesis, we should identify where our chemistries are. It can also help to identify changes. But we've got reactive sites there, and we have reactive sites there. Notice that the chemistry has moved. Okay? If we label our carbon as our methyl, in blue, our chemistry has moved downwards through the structure. Is there any single reaction that does that? No. For review, what are those reactions? Acid-base, substitution, elimination, addition, and radicals. Okay, so it can't be done in a single step, so what we need to do is start focusing on getting the chemistry to move. Depending on where you have a preference, you may decide to start at the reactants or the products. Okay, I'm going to start at the reactants at this point. The only reactivity I've got there is a pi bond, so I'm going to react the pi bond in what kind of a reaction? Addition, because I'm starting with a pi bond, there is only one reaction. It would be an addition. Okay? I want to put an extra hydrogen on at that carbon, and I want to put chemistry, keeping the chemistry to go internal. So in this case, what I'd be adding is H and Br. Those would be adding in the exact direction I want them to add. I want a hydrogen on that carbon. So there it is, as simple as HBr. I could now go through and reset and say, where is my chemistry? Okay, and compare to there. Okay, and we could run that same process. I'm going to show that we could also have gone backwards from our product. We ended with a pi bond with chemistry, which means our last step was probably the formation of said pi bond. Okay, which means I probably did an elimination reaction. And in elimination, what do I need? I would need a leaving group. That leaving group could go to either one of those two positions. Okay, so we could call them 1 and 2. Based off of where my starting material is, the more likely position is 2 than 1, because 1 is further than where all the chemistry started. Which means I'm going to place the leaving group at position 2, not at position 1. And for a good leaving group, bromine's pretty awesome. Okay? How would I get that elimination to occur? I have a leaving group. I also have to remove a hydrogen. Note that I have to remove a hydrogen to form the less substituted double bond. Okay? That would be a challenge. That's going anti-Zaitsev, also known as Hofmann. To get a Hofmann elimination, sterics become a very large play here. The reagent I would need would be a bulky base. OT-butoxide works great. Right, or works as best as we can expect. Right? We're now showing how those pieces could connect. If we go through and look at those, are those the same structures? Nope, which means chemistry is going to have to continue to move. I have to somehow show how I can get these two aligned. Okay? Both of these lack pi bonds, so I can't do any addition reactions. Okay? But I could potentially, we have to think a little bit carefully about that. This one, I can't do an addition reaction with because there's no pi bond. Could I have done an addition reaction here?
Yes.
Yeah, okay. That is possible because that is saying that I could have started with a pi bond. Where would I have placed that pi bond? Think back to the chemistry of the structure. I like where you're going. The chemistry is on that right-hand side. Okay. Could I have done an addition like that? Okay. That's getting the chemistry to go upwards where I needed it. Okay. That, if I did an addition, could put the bromine on. Okay. What would I be adding? Exactly. I'd be adding a hydrogen and a bromine. Okay. How would that hydrogen and bromine add?
Anti-Markovnikov.
I need it to add anti-Markovnikov. Is the addition of HBr an anti-Markovnikov addition? No. How would we know that? I could draw out our resonance structure for this guy. The best resonance structure puts the positive on the inside, negative on the outside. It would place the bromine in the wrong spot, right? That does look kind of familiar though, doesn't it? Yeah. So let's hold on to that one and still focus on this addition. I need it to go anti-Markovnikov. I need to add H and Br, but I need to add them in a fashion that goes counter to what I want to happen, or counter to what I would expect to happen. I would need to add roar, which I think is what I heard you saying too. Okay.
No, I'm just going roar.
Appreciate the sarcasm. All I was going for was radical. But roar works also. Okay. So that would complete that addition step. Okay. That resonance helps us to see that HBr, if we'd added HBr, that would have put the bromine there. Oh, that looks like the starting material. Can I go from this red structure to that blue structure? What would need to happen? Red to blue. I guess officially I should show it in purple, right? What kind of reaction is happening there?
Elimination.
An elimination. Can that happen in a single step? Yeah, so I need to do an elimination. What do I need to run an elimination? You need a leaving group. Do I have one? Yes. What else do I typically need to do an elimination?
Form a double bond.
Form a double bond by doing what?
Pulling off a proton.
Pulling off a hydrogen. So typically we would add, with our elimination, we would add
Strong base.
a strong base. We saw an elimination before with a bulky base. Should I write bulky base? No. If I run a bulky base, what happens? I would go back to where we started. I actually want the standard more substituted pi bond. I don't want a bulky base. I could do something like sodium hydroxide. What's the problem with sodium hydroxide? Could act as a nucleophile. What mechanism would it run? This is very rapid fire, by the way, in case you were wondering. SN2. What substrate do I need for an SN2?
Primary. Tertiary.
I need primary. What substrate do I have? Tertiary, which means no SN2. The only thing I get is elimination. Hydroxide is a fantastic reagent.
Cool.
Okay? Through all of that, we're addressing where the chemistry is, picking a reaction type. We then run that reaction type and say what things are missing to figure out what the reagents could be. Once I've got a potential reagent, I've got a structure that I could start with, and the whole process cycles again. Where's the chemistry? Where does it need to go? How do I cycle that? I can start at the reactant, I can start at the product. Either is fine. Okay? For this one, we showed both. Okay? They don't have to happen individually, they can happen simultaneously as well. Kind of makes sense? Okay, is it challenging? Yeah. Synthesis is one of the hardest aspects of OChem. You have to take all of this knowledge, instead of having it compartmentalized, be able to apply it to an overarching, bigger question of being able to see all those individual pieces and plot them out and move them. Okay? The biggest part of that is actually writing stuff down so that you can see that work. Kind of make sense? Okay. Part of that was knowing what our reaction types were so that we could start to create classifications to see that the chemistry couldn't just jump from one spot to another. Okay? I had to go in sequence. Are there other syntheses that would have worked? Yes. Okay? This just happened to be the one that we saw. On an exam, what I expect you to do is pick a synthesis and run with it. Okay? And do it to the best of your ability. Okay? And as we discussed before, you can very much decide synthesis is not your cup of tea and you're going to decide to ignore it for the rest of the semester. You just have to accept those as points. That's fine. I understand. Okay? So let's go from one exciting thing to another. Our spider diagram, we've pretty much covered everything up there. We've got our borohydride, our lithium aluminum hydride, our Grignard with the MGBR. We didn't really discuss the lithium, the organolithium reagent. Okay? It fits in the Grignard category, so we didn't push it all that much. That reaction is so reactive, or more so reactive than a Grignard, that it tends to do some other chemistries as well, like acid-base chemistry instead of direct addition. And then we looked at our Wittig. Okay, so things that we've missed. We haven't talked about the acetylide. We're not going to push that one. Okay, so I'm going to leave that one for you to decide or work through. But what that does open up is this massive branch downwards. The big thing that changes here is now we're no longer going to look at just a carbonyl. We're going to put a carbonyl next to an alkene. Okay? That's going to change the reactivity of the carbonyl. Why would it change the reactivity of the carbonyl? There's a resonance contribution. Okay? What does that resonance contribution do to that positive electrophilic carbon? It stabilizes it. So our electrophilic carbon becomes less electrophilic. At the same time, what does it do to the other carbon?
Makes it more electrophilic.
That carbon now becomes more electrophilic. This creates a problem. We now have a substrate with two electrophilic sites. What's going to dictate where our nucleophile attacks?
Sterics.
Kinetics versus thermodynamics. Okay? Sterics plays a part, electronics plays a part. It's ultimately going to look at the strength of the nucleophile. Right? So if we go through and take a look at this, chapter 17 was our strongest nucleophiles, right? Where I don't think I've referenced it in this terminology this semester, but are stupidly strong nucleophiles. Hydride, carbide. Okay? So all of those reagents up top tend to directly attack the electrophilic carbon, or our carbonyl carbon. Why? They are so stupidly strong that they're going to coordinate with the most positive atom. Why is the red one more positive than the blue one?
Induction.
Sort of induction, elaborate.
There's a polar pi bond.
It's closest to the oxygen, right? The carbonyl carbon is going to be by far more positive than that blue one. Okay? There's an inductive effect that makes the blue one an electrophile, but that same inductive effect is stronger for the red one because it's closer to the electronegative element. Okay? So we're going to try and neutralize those negatives of our stupidly strong nucleophiles as quickly as possible. What if we just have a strong nucleophile? Well, strong nucleophiles will now attack the other carbon. How did we know we had a strong anything?
Charge.
It was charged. What's going to make it stupidly strong?
Something that shouldn't be charged.
Something that shouldn't be charged. Okay? Hydrogen and carbon. Okay? Ultimately, there's a line. Okay? If it was just single elements, that wouldn't be too bad. We'd probably be okay with that. Anything that was a negative hydrogen or a negative carbon, stupidly strong. Negative nitrogens or oxygen are now just strong. Okay? That line is at least crystal clear through division of elements. It's not so clear. Okay? That line drifts through the carbons because we can get carbons to be stupidly strong. We can also get them to just be strong. How? Change the chemical environment in which they're in. Right? And we can already see that when we look at the Gilman reagent, another named one. The Gilman reagent follows the strong nucleophile, not the stupidly strong. Okay? So, carbonyl next to an alkene, two reactive sites. Okay? So now what we're talking about is how does this react? How does this affect our overall process? So we already drew out those resonance, so that shouldn't be a question. Okay? And now we're seeing this division. So what we have to do is decide, why is there a division there? Right? What would be the energetics between each of those pieces? Operative word being energetics, which means energy diagrams. We would need to evaluate thinking about energy diagrams. Right? So here we've got an overall reaction set up. We've got red arrows, we've got blue arrows. Right? Typically better about color coding. I did a pretty awful job color coding this one. Not to drop any hints. So if we go through and take a look at the nucleophile, I'm leaving it as neutral. Why? Because I don't want to open that bag. Ultimately, it's probably going to be negative, okay? Because it's either strong or stupidly strong, but it doesn't have to be one of those. We've got one option where it attacks the carbonyl carbon. As it attacks, it's going to break that carbonyl pi bond open, and we're going to end up with a negatively charged oxygen. Okay? Just like the Grignard did, similar to what the Wittig did, just like sodium borohydride, just like lithium aluminum hydride. But as soon as I add that alkene, I have another site of reactivity. The nucleophile could come in, and it can shuttle electrons by attacking the alkene. This should immediately send off some weird alarm bells for you. Why?
Negative's not at the oxygen.
The negative charge isn't at the oxygen. Okay, so if we just evaluate our initial result, we're putting a negative charge on an atom that doesn't like to have a negative charge. So we might say, well, that's a bad option. Why else might we look at that and be like, that's really weird?
You have another nucleophile.
What do you mean?
Well, you have those electrons that can react with something else.
So your claim is that these electrons, which I didn't show the electrons are, could act as a nucleophile. Couldn't the oxygen up here have just as likely acted as a nucleophile? Yeah, so I don't accept that one.
But isn't carbon less electrophilic? Does that make it-
That's making an argument between the stability of the negatives, okay, which we've already established. That negative carbon is not stable. You should have another problem with this. We just did a reaction with that structure, right? What did we react with it? What did it produce? What was the very first thing that happened? We were to draw out a mechanism, because all we've done now is draw a product.
The alkene pulls off a hydrogen, or bonds with a hydrogen.
Bonds with a hydrogen. Forms that bond, and now we have that carbocation, right?
Mm-hmm.
What did the alkene act as?
Nucleophile.
I'll sort of accept a nucleophile in that it's donating electrons, but what did it donate electrons to?
Acts as a base.
Okay, it donated to a hydrogen, so calling it a base is better. Ultimately, I was going to go to the nucleophile route anyway. The alkene acts as an electron donor. What's weird about our alpha-beta unsaturated ketone reaction in blue?
It's an electrophile.
The alkene is acting as an electrophile. Okay? According to all chemistry of alkenes we've seen, that should not happen. They're nucleophiles. We're getting a nucleophile reacting with a nucleophile. That is problematic. Okay? So that should be the reason why that mechanism doesn't make sense to you in blue. How is it different from the black structure, though? What is different about our alkene down here versus our alkene up here? Say that again? Resonance, it's conjugated with the carbonyl. What is that carbonyl doing?
Stabilizing it.
It's withdrawing the electrons from the alkene, making the alkene electrophilic. Okay? So on its own, an alkene should act as a nucleophile. Because we have attached it near a carbonyl, that ends up changing the chemistry. How much did it change its chemistry? What kind of nucleophiles are we talking about attacking it?
Strong.
Strong and stupidly strong. That alkene could still potentially be nucleophilic, but we're reacting it with such a strong nucleophile that it's forcing the chemistry the other direction. Okay. So, our blue path, we form that negatively charged carbon. Okay, what you guys all said was bad. We don't want to do that. Except what else should we consider?
The environment?
Environment's not quite going to help you. Resonance, which might be where you were going, but not quite specific enough. We can do resonance to put the negative charge where? On the oxygen. If we now compare our intermediates, a double-headed arrow is a bad idea there. I don't know how to compare those. We're going to circle them. When we now compare those intermediates, do we have a difference in stability? Okay. They're now both negative oxygens. Okay. Which of them would you expect to be more stable? Top one or the bottom?
The bottom one.
Why?
Alkene.
For resonance. There's a resonance stabilization. So we initially looked at that blue one and said, no, we can't form it, which would suggest it should be very high in energy. And then we shift to resonance, and what happens? Oops. Okay. That resonance effect stabilizes our blue reaction. Which means what about its energy? It should be lower in energy. Mustafa?
You said that.
What?
You said it was bad.
You guys didn't tell me it was bad? Oh, okay. Well, I intentionally misled you then. Hi?
Yeah.
So we end up seeing the blue one being a lower energy intermediate than the red one.
Can you just do the resonance to find the first word?
Resonance for first worst what? What are you trying to target?
So off that first structure,
Yeah.
structure, you can figure out that you've got two positive sites because you either do
So which positive reacts?
both of them.
When you run a reaction, you get one product.
Oh.
Okay? And that's what we have to evaluate. When we run with stupidly strong nucleophiles, I get one product. When I run just strong nucleophiles, I get the other product. So yes, looking at the resonance structure allows us to see there's two electrophilic sites. That's what we talked about when we looked at those resonance options. The question we've now got to decide is how does that dictate, how does that translate through our reaction?
Which one's the blue one?
The blue one is our blue path. So this would be intermediate, what do I call it, 1. This is intermediate 2. We look at our final answers. We have 2 alkenes, right? Which alkene is more stable than the other? Red or blue?
The blue one.
The blue one, because
It's more substituted.
more substituted. Okay? If we attempted to draw in arrow or curves, don't do it for this one yet. We might see something like that and not seeing a big difference in there. Okay? Which means, shouldn't we only get the thermodynamic? Okay? The other part that we have to factor in with this is where is our nucleophile going to be most attracted? Most positive or least positive? The most positive, which means our nucleophile is already going to be aiming for our carbonyl carbon, which means the transition state for that red one is significantly lower than for the blue one. That's where we get our differentiation. So when we talk about kinetic or thermodynamic, we have to have a crossover point. That's where the crossover point is. Everything afterwards, downhill, not a big deal. We don't see a differentiation between them. Our crossover happens in that very first step because that carbonyl carbon is the most positive. All nucleophiles are going to go to that position. Right? So with that, what do I end up with? The red one ends up becoming my kinetic product. Why is it kinetic? I'll accept two answers. Produce first, or it happens fastest. Okay. It's a weak tie. You should be able to do better than that. Why does it react faster? The activation energy is smaller than it is for the other one. Why is the blue one the thermodynamic? It's lower in energy, it's more stable. Okay? So this is the basics of our reaction. We haven't elaborated what the nucleophile is. If you change the nucleophile, how is that going to change your overall reaction?
If it's stupidly strong, when I go faster because it's less stable. It's just like
Okay? It is less stable. How does that change our energy diagram?
It'll increase the energy.
It'll raise the energy. It'll raise the energy of what?
Your product, your intermediate.
Where does the nucleophile show up? Look at your mechanism. Where does the nucleophile actually show up as a nucleophile?
The reactants.
It's the reactant. If we have a stupidly strong nucleophile, that makes it less stable, which means if I now factor the strength of the nucleophile into this, what happens to my reactant energy?
much higher.
It goes up. How does that change my reaction? Okay. Well, if we're looking at this version of it, okay, since we didn't get a change over here, and yes, I just erased kinetic. That was stupid. What happens if we run the reaction again? Okay, here's still our kinetic. I don't know if it bothers you, but it really bothers me that I screwed up the color coding on this. The thermodynamic. If we now switch this up to a stupidly strong nucleophile, what happens? You'll notice that I just erased some stuff that's up high, right? Here's our reactant energy now. The kinetic is still going to have a lower activation barrier. Thermodynamic is still going to have a higher activation barrier. What now changed about this?
The energy required.
What energy required?
To run the reaction.
Really? You're saying the EA here versus the EA here are really all that different?
No, the reverse is way
The energy to run the forward reaction probably doesn't change much. If anything, when we move to the stupidly strong one, that energy probably shrinks because we now have a stupidly strong nucleophile. But what is the major change? The reverse activation energy skyrocketed. Okay? Remember, second semester Gen Chem was all about equilibrium. Guess what second semester OChem's about? Equilibrium. If we look at our energy differences here, the reverse reaction is relatively possible to happen. I'm always going to form the kinetic product first because it has the lower activation energy. If there's enough energy or time given to the reaction, that reaction will reverse back and establish an equilibrium. Some of it will go to make thermodynamic. What's the problem with the thermodynamic product? It won't reverse as easily as the kinetic. which means the instant I form thermodynamic, I'm now pulling reactant out of solution. If reactant comes out of solution, what does the thermodynamic product or kinetic product do? It reverses to make reactant. Some of that reactant makes it to thermodynamic. I've again removed reactant from solution. What does the kinetic product do? Reform reactant. So when our products of that initial step are close in energy to our reactants, we get a reversible reaction. But what happens when I shift to a stupidly strong nucleophile? I'm still going to form the kinetic first. It's still going to have a smaller reverse activation energy. But that activation energy is really, really high. So the likelihood that I can reverse from the kinetic product goes to near nothing, which means the only product I get is kinetic product. So what I have to be able to do is to look at that reaction and say, well, one of those results in kinetic, one of those results in thermodynamic. And I have to decide, am I stupidly strong or am I just strong? I have to be able to look at a reaction and predict how much product should I make. Is that a reaction that's likely to form product or is it not? Okay? That is a challenge. It's also one you guys have already done, which we'll talk about in just a second.
Are there any, because that looks very exothermic. Does that cause any problems?
Yes. It is exothermic, which means what's it going to do? It's going to off-put a lot of heat. That heat can cause other side reactions and other issues going on. Typically what's happening, though, is that in your kinetic system, you're also typically running it at heat. If I give this heat, what do I increase the odds of happening?
Thermodynamic.
Getting the thermodynamic. If I want the kinetic, it's usually run under cold conditions. You mean the same cold conditions that when we talked about the addition to a pi bond with HBr, we said kinetic we wanted cold and thermodynamic we wanted hot? You mean the exact same conditions translate to this? Yes, they do. It's nice when that happens, huh? Okay. Okay. So, where have we seen this before? I've got HCl and H2O. Okay, and we'll actually simplify this out a little bit. Let's do HCl. We'll do HC2H3O2 plus H2O. Yeah? These look familiar to you? They should look incredibly familiar to you because you've probably written them out tens, if not hundreds of times in Gen Chem. Right? Because you study acetic acid and HCl very commonly. Right? They should look familiar enough that you should immediately be saying there's a typo in the very first one. What's the typo in the first one? The arrow? What do you mean the arrow?
HCl is a strong acid, so it should go only in the one direction.
Why do you know that?
Because when you form.
pKa. You mean you memorized a numerical value to tell you that HCl? Okay, so you're telling me the pKa of HCl is what? Larger or smaller than the pKa of acetic acid? Smaller. What is the pKa of HCl? Okay. What is the pKa for acetic acid? So you didn't memorize pKa's. You just know that there is a difference in pKa's, and you could have used that to predict this. And yes, you absolutely could have. The pKa for HCl is a -7. The pKa for acetic acid is, I think, 4.25. Maybe even 2.6. I think it might be 2.6. Somebody got yelled at during an interview. It wasn't me and wasn't by me. I thought I was stupid. Okay. 4.26. Which one's the stronger acid?
HCl.
HCl, because smaller pKa. Right? So we could go through and try and evaluate that. So that tells us HCl is the stronger acid. How do you know HCl is unidirectional? That it only goes to form products?
Because you can't form it again. It dissociates.
I memorized the 7 strong acids.
Right? Most of you probably memorized that HCl was a strong acid and just walked away. Yeah? Perfectly acceptable. Okay? That is a reasonable thing to do. Okay? What could we use to further evaluate this? We could look at the pKa of our products. What is the acid on the product side for the HCl reaction? H3O plus, which has a pKa of negative, it's 1.7? I was going to say 5.
I thought it was 3 overall.
What did I write? 1.3. So there we go. Let's just assume that I was smart.
Okay.
HCl to H3O plus. Which one's the stronger acid? HCl. We know that because it has a smaller pKa. Okay? Which would you rather have thrown on you? And I know this is a horrible face test. Okay? Because it is HCl, a strong acid, and H3O plus, arguably a very strong acid. So both of these would be horrible. But which one is going to cause theoretically less damage? H3O plus. Chemistry does the same thing that we do, and it's going to shift away from the more reactive species. So it's going to shift to form a high concentration of the H3O plus. Right? How much? Remember, pKa's are logarithm scale, so these are powers of 10. So 7, what is that? 5, 10 to the 5th difference in concentration. That's pretty phenomenally huge. Yeah?
10 to the 6th.
Whatever, I can't count. If we go to the other one, what do we notice? Which way should the equilibrium go? It should go to the reactant side. Okay? So we could use pKa's to do this. You did this in 152. But to do that, what did you need to know? pKa's. How many pKa's have you memorized?
0.
Okay, so I wonder if there's another way to do this. As a hint, there's 5 things that you should be looking at. Charge, size, electronegativity, resonance, and induction. We're looking for our electrons. Is HCl supplying electrons? No. So where should we be looking? H2O. What are we going to compare it to? Cl minus. Okay. Some of our strong acids generate problems because we would try and balance out with charges. This is where the strong acids do weird stuff to us. But we could try and compare charges. As soon as we shift away from the strong acids, right? Because like the strong acids are tricky. So what do we do to you? What do we do with you when it comes to things that are tricky? We tell you to memorize. And what did you do with the strong acids? Oh, you memorized them. I wonder why. Because, by golly, they're tricky. Let's switch to the other one. H2O versus C2H3O2. When we make that comparison, which one's more stable? Because it's neutral. First rule right out of the gate tells us the reaction favors the reactants. Do I need to know anything about pKa's? No. You don't need pKa's to make these conclusions. You can just use those same rules: charge, size, electronegativity, resonance, and induction. This is why I told you to memorize them. This is why you'll see it again on exam 2, but you'll see it in a trickier fashion. Okay? And if I have to ask it on exam 3, just so you know, on exam 3, it will result in a loss of points. Meaning you could get a negative score on exam 3 if I have to ask those questions. Does that make sense? Okay.
Booby trap, right?
What's that?
That's a booby trap.
It is. Okay? So when we go through and look at this reaction, which of those steps did we say was the most important to evaluate? Steps. There's 2 steps there. Which step did we say was most important?
The first.
The very first step. So I don't care about this last one. We'll get rid of it. What am I going to be comparing?
Stability.
Of?
The nucleophile.
The nucleophile, yes, to? There's only one thing drawn there.
Product.
That product, yes. Which part of that product?
The oxygen.
Why'd you pick the oxygen? Good man.
Got the charge.
It's got the charge. There we go. So I'm going to compare the nucleophile to that oxygen. Which of those is more likely to hold the charge?
Oxygen.
Oxygen. Okay. Which means? More stable, which means? Not equilibrium. Irreversible. Grignards. Where do they attack? Right there. They don't reverse because they form a more stable product. What happens if instead of it being, I don't know, carbon, I make it a negative oxygen? Which is more stable, a negative oxygen or a negative oxygen?
Negative oxygen.
They're the same, which means I get an equilibrium. What does the equilibrium mean? Instead of getting the kinetic product, I get the thermodynamic. So if I can establish the relationship across the reaction of my nucleophile to that negative oxygen and then decide which one was more stable, or if they are the same stability. If they're the same stability, I need the thermodynamic product. Okay? If the negative oxygen is significantly more stable, then I get the kinetic product. Okay? That's the big black and white picture. It's not black and white. Okay? Because we do hit some pretty big gray areas that we just ultimately are going to have to memorize. Okay? There were some references to pKa. Horribly done. I apologize for that. Should not have been referencing pKa's because the pKa's make it confusing. Why would the pKa's make it confusing? pKa references what species?
Acids.
An acid. What species carries a negative charge? A base. Or a nucleophile. Neither of them are acids, so when referencing the pKa's, what would you need to do officially if you wanted to look at numbers? You would have to convert them into pKb's. How many people liked pKa's to begin with? How many people like converting pKa's into pKb's? No, so what should we do instead? Charge, size, electronegativity, resonance, induction. Right? And then the small cases where we get counter arguments, those we'll manipulate on an individual basis, and we'll try and memorize those. Okay? Cardi put it together nicely. Okay? Again, we've got those pKa references down there. Again, bad idea. Okay? But what I tried to show was our big difference. Okay? With that other energy diagram. If we go to stupidly strong, our reactants are much higher in energy. God, that looks ugly, but whatever. Okay? And that changes the reversibility of the reaction. Okay? So you will hear these reagents labeled as reversible or irreversible. Okay? That's what they're really talking about. They're trying to get you to think about how are they reversible and irreversible, and then ultimately what product does that lead you to? Okay, so what is, a lot of the pKa references. So Cardi comes up and gives you a table and says nucleophiles that add reversibly, nucleophiles that add irreversibly. All of them are negative, so they're all strong. The very first one on irreversible is which reagent? The Grignard. I don't know why I wrote Grignard there because that's totally illegible. Actually, that's not too bad. What's the reactive species? What atom is reactive in the Grignard? What is the R? A carbon. Negative carbon. A negative carbon in comparison to a negative oxygen. Which one's more stable? The oxygen. By a lot or a little? By a lot. What does that mean?
It favors the oxygen.
It favors the oxygen in what fashion? Irreversibly. Notice what does Carty have at the top of this table? The word irreversibly. Said in Mike language, the stupid strong nucleophiles. When you go through that list, all of those end up being stupidly strong nucleophiles. Okay? Those should be relatively straightforward. And you might be, okay, I can accept that. What's the very first one on the reversible? A strong nucleophile. What atom? Oxygen versus oxygen. Which one's more stable? They're the same, which means reversible. So these ones are just our strong. Okay? I finally just remembered what word I wanted to add on top. So these are going to be our thermo. Okay? Next one, nitrogen. Which one's more stable? Nitrogen or oxygen? Oxygen by a lot or a little? Only a little. Nitrogen's still pretty electronegative. I can form a negative nitrogen. Halogens. Okay? Arguably more stable again. Okay? Next one, another oxygen. Next one. That's a negative carbon, isn't it?
Yes.
And the next one down? Negative. I thought carbons were irreversible. We don't need to show that as a hydrogen. Keep showing it as a hydrogen. Isn't a negative carbon stupidly strong? Except when I draw out a resonance structure, where's the negative charge? On the oxygen. Which is more stable? Oxygen or oxygen? They're the same. That last structure, due to resonance, is a weak negative, a weak strong negative. You gotta love the word there. Okay, or not stupid. Let's try that. Okay. How about the cyanide? Because there's no resonance on that one.
Induction.
We could make an inductive argument because the nitrogen is inductively withdrawing electrons from the carbon, making the carbon less negative. Okay? More neutral. The more neutral it becomes, the more similar in stability it comes to the oxygen. You can use pKa arguments for these two and compare them out to water. Okay? And you'll find the pKa's all fall pretty darn close to each other that you could use a pKa argument for those. I would argue the enolate, which is that last one, you shouldn't memorize because you know resonance. The cyanide, I'd memorize. Okay? There's another negative carbon that we could throw up on there. The acetylide. Okay? When we get into carbons with those negative charges, sometimes they add reversibly, sometimes they add irreversibly. So you have to walk that line a little bit more carefully, which means you ultimately have to have that line kind of memorized. Okay?
It's also your, not just inductive, but it's also the
Use the word, yep.
bonding. Hell, I can't remember the word right now.
Mustafa's favorite. Hybridization.
That's the word.
The hybridization on that carbon is sp that changes its electronegativity, which means the difference in electronegativity of the carbon and the nitrogen isn't so large, which means the carbon's less negative. Okay? So this is 1,4 versus 1,2 additions, okay, which is really just a fancy way of saying kinetic or thermodynamic. Okay, all of that's ultimately a nomenclature aspect or a naming aspect behind running these reactions. Kind of, sort of? Okay. So, sorry, come back here. Yes?
With the, if you were to make the hybridization argument, could you just say it has more S character?
Yes, it is more S character.
So that's why it's more stable.
Yeah. So, in all of these cases, we have a carbonyl at the alpha beta position. I have unsaturation. So if you see an alpha beta unsaturated carbonyl, you should be thinking about 1,2 versus 1,4 addition. What are those referencing of numbers? All right, let's go through and take a look. There's that carbon. Where did it end? All right, well, that's 1, 2, 3. Okay, what's the other one? 1, 2, 3. So there it added at position 1, right? Okay, well, how is this counting system working? The counting system is not a nomenclature system. Yay! Okay. If we look at this reaction, we are adding that carbon structure. What else are we adding to the structure? Okay. This one is easier to see. Yep, just heard the answer. We're adding the carbon and we're adding, sorry, I stuttered as I drew that one, a hydrogen. If we look at the other one, I did it again. Oh well. We added our carbon and we added a hydrogen. Where did we add the hydrogen?
Position 1. Position 2.
We added it here. All right? You don't have to trust me on the numbering yet. We'll get to that. But is that where I added the hydrogen?
Yes, you had to.
Okay. So let's take a look at the one that's boxed, because that one's a little bit easier. Okay, because if we look at the one that's unboxed, pretty much any way you number that, 1, 2, 3, you get a 1, 3, not 1, 4. It's definitely not 1, 2. Or oops, we could get a 1, 2, right? 1, 2. Okay. But then the other one is also 1, 2. So the numbering system here becomes a little bit weird. Okay. So it's a little bit easier with the one on the right. So let's do that one first. The numbering is going to start at our carbonyl. 1, 2, 3, 4. So when we look at the one in red, we have a 1, 2 addition because we added it to the oxygen and to the carbon immediately next to it. So this is a 1, 2 addition. The 1, 2 addition happened to be which product, kinetic or thermodynamic? Okay. That's an important one to address. We could think back to our mechanism behind it. Okay. The other thing we could look at is which tautomer is more stable, the keto or the enol form? Keto. So if I see a ketone, I should be thinking, if it's more stable, thermodynamic. Do I see a ketone in the red box?
No.
No, which makes it the kinetic. So that must mean that this other one has to be a 1, 4 addition. Right? And thereby thermodynamic. We counted out 1, 2, 3, 4. Where did I add my hydrogen and my carbon?
3 and 4.
3 and 4. So I got a 4, but I definitely don't have a 1. I could also have counted that the other direction and gotten 1, 2 as well, right? So what the hell is going on with that one? Okay. Helps if we break down the mechanism a little bit. Attacks. Attacks. There's our ring. Is a carbon stable? A negative carbon stable? What does it do?
Reacts with the.
We have to show resonance. For those of you being like, do you really have to show resonance? Do you want the mechanism right? Then yes, you have to show resonance. We're not allowed to do a step if it's not a stable step. I'm putting the negative charge on that oxygen. What could I do to stabilize that negative oxygen? I could protonate it. So I could add my H+. Where do I add my hydrogen? Oxygen. Try again. Give me another identifier. Like there is no other identifier. I know, I erased it. 1, 2, 3, 4. I added my carbon, I added my hydrogen. Where did I add them? The 1 and 4 positions. Unfortunately, what functional group did I form? An enol, and what does the enol do? Tautomerize to give you the ketone form. It's still a 1,4 addition, but the 1,4 addition product goes through a tautomerization that hides the 1,4 addition chemistry.
Is that
Okay.
where your water comes in?
Yeah. Okay. Enols are important. Okay. But that's where the name 1,4 addition is coming from. Okay. It also helps us to establish that thermodynamic stability, because if we look at our alkene here, this is a more substituted alkene in green than it is up in our red box. So that makes it the thermodynamic. Okay. So our cheats behind this. If you see a ketone, it is the thermodynamic. The other one would be your kinetic. It says, since, man, word I want to start with. I believe because. Because most of your test is multiple choice, guess what 2 structures you're likely to see. A ketone, an enol, and just the straight alcohol. So there's 3 structures that could show up. Immediately, what should you do with the enol? Cross it out, because what's it going to become? The ketone. You now have the ketone, which is the thermodynamic, or the alcohol, which is your kinetic. To decide which one's your correct answer, what do you need to evaluate? The strength of the nucleophile. In this case, which nucleophile did we start with? A stupidly strong. And a stupidly strong favors kinetic. Okay? I'm going to erase it all. Yep, just waiting for an objection. That's the one we get. How about the next one?
The alcohol.
We have our keto, thermodynamic. We've got our alcohol, which is our kinetic. What's our nucleophile? A negative oxygen. And we're comparing that to a negative oxygen, which says thermodynamic. There's no difference in stability for those, so I'm going to favor the thermodynamic product. Okay? It takes practice. Okay?
Wait, what did you compare?
What did I put what?
What did you compare?
Negative oxygen to a negative oxygen. Remember, we're talking about that initial nucleophilic attack, which generates a negative oxygen. Okay? What we're trying to decide is the kinetic result useful or not? Okay? In this case, we're saying it's not useful, so that's a reversible thermodynamic. Last one. I would again go through and label. Here's keto, which meant thermodynamic. Here's our alcohol, which means kinetic. What's my nucleophile? A negative carbon. Negative carbon versus negative oxygen, which is favored? Negative oxygen, which means kinetic. Anybody else notice something potentially tricky about the last one? If you go through and look at the sequencing, it went thermodynamic, kinetic, kinetic, thermodynamic, in the ordering of the structures. Okay? Don't fall into false placements of where those things are drawn out. Yes, Mary?
Isn't that stupidly strong?
Stupidly strong, and stupidly strong favors kinetic. Okay? Questions? Okay. HCN, I personally don't really care about. The reason why it's typically talked about is that when you run through the reaction, you maintain a lot of chemistry. Okay? Where this is going to be particularly useful would be like carbohydrates. You've got an acid and an alcohol immediately attached next to each other, the same carbon. That hydrolysis is ultimately the next unit, so don't stress about it. Okay, we'll see that in the next unit. Really, it's the cyanide attacking the carbonyl. Could we speed it up? How? Could add heat. Add an acid. Add a base. If you add an acid, what does the acid do? Protonate the oxygen, making the electrophilic carbon more electrophilic, more susceptible to attack. The problem with that is that this is an acid. For it to act as a nucleophile, what must happen? We have to break that bond. If we're under acidic conditions, does that bond break? No, which means no nucleophile. So what could I do to speed it up if I can't add an acid? Add a base. What's the base going to do? It'll remove that proton, making our nucleophile more nucleophilic. Okay. Our Gilman reagents. Okay. So the product does have a typo here. It's noted up there. That CH3 is supposed to be an ethyl. I apologize. Okay. What's the nucleophile that you see here? What does a nucleophile need?
Charge.
What charge?
Negative charge.
Negative. So where's our negative charge?
On the CH3, CH2.
Okay. It's that carbon. You notice it looks a little bit ugly, and that's because this copper reagent is coordinating two organic compounds on either side. Okay. So we get two negatively charged carbons. Okay. Very similar to the Grignard. We get a carbon-metal bond, which means I get a carbon nucleophile. What would you say about a carbon nucleophile? Stupidly strong or strong? Stupidly strong, which means what product would we expect? Okay, we would expect our kinetic product. We'd expect the alcohol. What product do we get? We get the thermodynamic. Okay? So what is our difference between Grignard and Gilman?
The metal used.
The metal used is the big difference. What is the difference between those metals?
Copper's a lot bigger.
So we could look at size. What is that size going to do?
It's going to stabilize the charge.
If it's bigger, that would weaken that connection, so it should actually make that more negative. I'm not positive on the size, but copper's probably not much different than magnesium. What is the big difference? Electronegativity. There's a significant difference in electronegativity. Copper's more electronegative than magnesium. What does that mean? If copper is more electronegative, what is it doing to the electrons in that bond? It's pulling them towards it, which means the carbon's becoming less negative. Less negative means less nucleophilic, which means it becomes just strong, not stupid strong. How would you know that? You would memorize it. I would really recommend memorizing the Gilman. Okay. It is actually so weak as a nucleophile that if we get rid of the alpha beta aspect behind this and just throw a carbonyl at it, guess what happens? Nothing. The Gilman won't react with the carbonyl at all. Okay. It needs the alpha beta unsaturation to actually get the reaction to go. Okay. So I would recommend memorizing the Gilman because being able to establish that its chemistry is different as a negative carbon is solely based off of reactivity. Okay, at least the arguments that I've given you. We don't have a way to quantify that easily. So you either memorize all the quantification behind it or you just memorize the Gilman is just a strong nucleophile, not a stupid strong. Okay. We definitely don't have time for synthesis because we're kind of done, but we'll look at those synthesis next class period. The next sequence that we're starting into, this I think has all of our nucleophiles on it. So carbon, oxygen, and nitrogen. The oxygen and nitrogen are the next chapter that we're about to move into. They suck. Okay. So if you thought carbon was difficult, the oxygen and nitrogen really bring in very heavily equilibrium, and that equilibrium makes things very challenging to deal with. If you've not watched the play posit video dealing with the weak nucleophile addition or the weak strong nucleophile addition, I would highly recommend you do so because we will be sliding through a whole bunch of slides that should just be review. All right, so if you've got questions, I want you to stop me early on those.